Previously, we have learned that poka-yoke, or fail-safe mechanisms, can eliminate defects at the source. This becomes especially important when we are to implement the flow production concept. For example, smooth one-piece flow production in a U-shaped line cannot be achieved without ensuring quality at the source. However, when simple poka-yoke can't solve the problem, further consideration must be given to improving the process capability so that we can establish a reliable production process and adequate quality control, or QC. The basic principles of QC we should remember are: 1. Our first priority is customer satisfaction. For all of the work we do has only one purpose: to satisfy the customer. We must always remember who they are and listen to what they may have to say. 2. Remember that QC starts with individual problem-solving activities. To paraphrase John F. Kennedy, ask not what your company can do for you, ask what you can do for your company. 3. Control must be based on the facts. Investigate the data available and look at each problem firsthand. Don't rely on the emotions or recollections of others. 4. Learn the basic techniques of QC. These include histograms, cause and effect diagrams, check sheets, Pareto diagrams, graphs, control charts, and scatter diagrams. These are often referred to as the 7 tools of QC. 5. Use the so-called PDCA cycle of continuous improvement every step of the way. PDCA corresponds to plan, develop a plan. Do, perform work as planned. Check, check the results for conformance. And action, analyze the results and take action for further improvement. 6. Attack or focus on key areas first. Instead of wasting a lot of effort on things that contribute little to a solution, concentrate your efforts on key areas, using the Pareto principle. 7. Control the factors causing uncertainty or scatter. If you can eliminate the scatter, you only need to sight in on the target. And 8. Report progress by sharing your QC story with others. After progress is made, share the results on a standardized form so that more employees can benefit from other people's positive QC experiences. The bottom line is that everybody can be a problem solver. If we need to depend on our inspectors to find all of the defects and our engineers to solve all of the problems, then it's already too late and too costly. Furthermore, doing this in effect is squandering the capabilities of our people. In principle, we should all agree that quality must be addressed at the source and by those who are closest to the problems. In fact, the same concept also applies to the quality of the managerial process. Understandably, if we are to meet our customers' needs, our own managerial processes need to be well under control in all areas of the organization.
This is our hand load line, and these people use statistical quality control to monitor the process quality in their area. This gives them feedback on the process quality so they can take action to improve their own process. And the wall you see behind me is actually the display of the process quality and statistical quality control tools for all our process centers. In particular, this is the wave solder process, and you can see here that we have short-term feedback, actually daily feedback on this X/R chart. We move down here and we see Pareto charts, so we can look at long-term trends over a number of weeks from week 5 to week 23. We're also able to look at defects found internal to the process and defects found at the customer in the next process in the flow is their customer. This is based, the Pareto charts here are quantity based, and then we also have a parts per million level of X/R chart. This wave solder process in particular has provided us with a real success story with statistical quality control. A few years ago, we had a quality level about 20,000 parts per million in this process. And through using statistical quality controls methods, we've been able to achieve an average of 2 parts per million on our wave solder process. But we're not satisfied with that. We continue to work on this process so that we can get it down to 0 parts per million.
Now, let's hear from the supervisor in charge of this area.
This chart indicates our customer defects, and in the morning, our operator collects all the data and plot it on this chart. And if we see a high peak, obviously we need to work on. And so we take action right away. And also we do have an ongoing continuous improvement team, which we can resolve this problem as well. So if we find out what caused that, immediately we go tackle that problem and try to solve that.
The Quality Circle program has been an excellent method for operators, lead men, and supervisors to be involved with the problem solving itself. After all, the people on the shop floor are much more familiar with the actual problems than management or people in the engineering group. Tapping that resource has been an excellent method for making improvements at TABC. These are some of the themes that have been finished in the past in the press room. So we have problems such as problems with a header board panel, or a rear skirt, or some of the other parts that are included within the truck bed. In solving a circle, there's a lot of work that goes into it, and I can give you some examples here. The Pareto analysis, the cause and effect diagrams, following the targets, doing additional studies before and the current situation, and diagrams to show exactly how some of the problems were solved.
So we can all learn the tools for problem solving.
Yes, and once you solve a problem, you may discover just how satisfying such an experience is.
Then is it a question of just getting used to it?
Yes, for that reason, managers need to be educated so that they themselves can use these tools and teach others. Then they should support people to learn to use these tools.
Japan's quality circles would be one of these activities, right?
Yes, but one thing we should all understand here is that it was not an easy process for them to develop the skills that they have now.
Well, so what you are saying is that it's not Japanese magic, but that they went through the same evolutionary process, and it was not necessarily an easy process for them either.
You're right. There's no instant pudding. There's a need for management support and encouragement. Also people's interest, pride, ownership. These things are necessary for making it a real success. And for this to happen, the Japanese have tried different things such as creating the Deming Award, the Japan Quality Control Award, and so on, and publishing numerous magazines such as these, and the books such as these. They are all important parts of developing a supportive environment for people to study these techniques and practice them. In fact, if you attend a Deming Award ceremony or any conference on QC or suggestion program, you'll be impressed by the attendees' serious attitude throughout.
Well, it sounds to me like they have tried to develop a supportive environment to learn these skills, almost like a national objective.
Yes, I think you can say that, especially when such activities serve the nation's interest too. But the last point I want to make here is that when we learn these techniques, these tools may not only help the organization and company, but perhaps, and more importantly, these tools can enrich our lives too.
Why is that?
Because the process of problem solving is universal to any environment. If there is a problem, there is always a cause and effect relationship. And since we have only limited resources, we have to prioritize or focus our efforts to solve the problem. And that's what we do throughout our lives anyway. Without recognizing it, I think we are going through a plan, do, check, action cycle in our lives. That's what I'm saying here.
I see.
Let's see an example of problem solving at FMI. As we have studied the line stop concept before, This example shows the use of problem-solving techniques to reduce the number of line stops.
We started counting how many times the line stopped and from every station, and that will tell us how many problems we had. And right here we started doing this chart, and process control, it helps us to see how many times the line stopped, and right here tells us how many, which stations, how many times every station did stop. It helped us realize what kind of problems we had, what kind of problems we can resolve first, and which problems that we could do at the beginning of the program. And the problems that we resolved, when we started doing that, the problems that we resolved, it went down from 493 times, went down to 133. From those kind of problems that we had there, we made a fishbone drawing, and right here we can see that from every station we have information of those amount of times that every station had to stop, and from that we can tell how many, the problems that we had. From there we can tell the problems that we had, drawing a chart and see which category we had to resolve: machine, man, method, and material. And once we put it in that category, we started resolving these problems. Okay, and from every station we have those problems drawn in here, and we can start now resolving them.
As our factory becomes more streamlined and inventory levels are reduced, we may still need to address problems associated with machine maintenance. In recent years, several sophisticated computerized maintenance programs have been developed to serve this purpose. However, without the combined efforts of the operators, management, maintenance crews, and other support people, effective production maintenance will never be achieved. An especially crucial step in achieving trouble-free operations is the early involvement of the operators. Because they run the machines, they have the first opportunity to sense any problems before serious machine breakdowns occur. We need to take advantage of this to address machine maintenance at the source, rather than by collecting the information after the fact. To facilitate this communication at Toyota Auto Body of California, a visual aid was installed to inform maintenance crews about the condition of the machine. So they called this a maintenance Kanban. Just as inspecting parts after the defects are produced can never totally eliminate defects, we cannot establish trouble-free operations without addressing the issue at the source. This shows an approach to preventing them. One of the key points here is the realization that people themselves are the cause of the problem. Typically speaking, machines do not create problems by themselves. Rather, people let machines break down, for example, by forgetting to oil, or retighten bolts, or by leaving the machine dirty, or perhaps by not following the proper instructions. As in the case of housekeeping, it's a matter of learning to discipline ourselves. Experience shows that most machine problems are not solved in the office. We need to spend our time on the shop floor, facing the problem directly. Furthermore, the process of questioning should be persistent, so that the problems do not recur. Simply by asking why 5 times, we may be able to capture and eliminate the true cause of a problem.
This is a group of different skilled tradesmen. We're called a Tpm Team, which stands for Team Plan Maintenance. We get jobs from production, and they're jobs that have ongoing problems that reoccur all the time. And we go out to the job, and one of the things that we do is try to use the 5 why system, where we ask why. One of the machines we went out to was an Excello, and we asked them what the problem was, and they said it was vibration. So we asked them why did they have the vibration, and they said it was because they had bearings that went out on a every 6-month basis. We asked them why that happened, and they said it was because they put new cylinders on the machine. And we asked them, well, why did that cause a problem? And in our investigation, we found out that the cylinders were not true, weren't balanced. So we took them off and balanced them, and the
the machine has worked well ever since.
Again, I hear common sense, discipline, and people involvement as the basic approaches for proper maintenance.
Yes, an important point to notice here is that machines do not break down by themselves. Generally speaking, people force machines to break down.
Well, why is that?
Because we may not lubricate the machine as required. We may not retighten bolts when necessary. We may not do anything when the machine starts to make noise, or start to vibrate, heat up, leak, or we may not follow the right operating procedures. These situations should not happen if we care about the machines.
So people should take more care of machines by themselves.
Yes, for example, cleaning up machines is basic. This way you notice potential problems better. Or operators can do lubrication, or retightening bolts may be another basic point. In fact, in one automotive parts factory in Japan, after retightening bolts, the machine problems were reduced almost 80%.
Oh, it's amazing. But what do you think of advanced computerized diagnostic systems?
If the basics are well taken care of, it may well be worthwhile. But if, for example, operators are not following the operating instructions, or if prescribed maintenance procedures are not followed, I will feel very uncomfortable using any sophisticated system. I think we need to address the root cause first.
Well, that makes a lot of sense.
I'm sure we still have a number of employees who are not really into their job. We've begun this program in earnest probably 4 or 5 months ago, and we've turned around some employees. I don't think we've got them all yet, and we may never get them all. But if you can take a department of 20 or 30 people and get even 10 or 15 of them to think and want to make things better and contribute, that's a heck of a lot better than having none of them contribute and none of them think for you. So you may never get everybody in that utopia, but I'll take the 10 or 15 that are really going to help us.